So for first order reactions means that rate is equal to K concentration A power 1. So is also equal to negative change in concentration of the reactant A over times. So when we combine these equations, we can get the constant K is equal to change in concentration A over time T multiplied by concentration A, so that we can get these equations, which is ln concentration A at any time over the initial concentration of A and equal to negative KT. So when we integrate these equations, so from as concentration A at time 0 to concentration A at the final, so it is equal to dA over A and equal to negative K at from 0 to T dt. So we can get these equations for the first order of the reactions. So for the first order of the reaction, the concentration T, when you plot the curve, concentration T versus T, so you can get this kind of curve. And then when you replot the equations, when you rearrange the equation following the y is equal to mx plus c, by plotting the ln A concentration E at time t versus t, so you can get the straight line curve with the slope of negative k. Okay. For example, the composition of nitrogen dioxide. So you can calculate the rate of reactions according to the first order of reaction. So when you relate the first order reaction with ideal gas equations, so from ideal gas equation, PV is equal to nRT. So N over V is equal to P over RT. So from this equation, which is ln concentration T at time T over concentration initial concentration is equal to negative KT. So then we replace the this one A, which is concentration A is equal to NV, okay, which is equal to P over RT. So we replace to this equation. So finally you can get this equation, which is ln PT over P naught equal to negative KRT. Then therefore we can rearrange this equation. So we can plot the graph ln PT versus T. So half-life for the first order reaction means is from the initials, how time taken for the concentration to reduce half from the initial concentration. It enables us to estimate the magnitude of the rate constant, which is for example, the shorter the half-life means that the larger the value of the constant K. So the half-life for the first order of reactions means that the time taken from the initial concentration to be half, okay, which is concentration of T, which is any T, is equal to the A naught or the initial concentration over 2. So from this equation, so we rearrange these equations. So T is equal to 1 over K ln A naught over AT. So we replace AT with the A naught over 2. So we can get that ln 2 is equal to KT half. So T half is equal to ln 2 over K and equal to 0.693 over. Okay, you can see this figure at time 0, which is this is the initial concentrations, and then at 1 minute, which is the T half from the initial concentration, which is 50% reduction in the concentration of A, while after 2 minutes there are another half or 50% reduction in the concentration of A. Okay, for second order of reactions means that the rate of the reaction is depends on the reactant concentration raised to the second power of the concentration of the different reactant. So for the type 1 means that the different two different concentration of the similar similar types of species. You have A and A to produce a product. So the rate of the reaction is equal to K A concentration of A, K A and A, so K A power 2, and it is equal to change in concentration of A over T. So when we combine this equation, so we can get K is equal to A concentration A over AT A power 2, and the unit of K for second order of reaction is equal to M minus negative 1 as negative 1. Therefore, when we want to get a Y is equal to mx plus C, by plotting 1 over A T versus T. So for second type of second order reaction, for example, you have a different reactant A and B react together then to form a product. So the rate of reaction is equal to K constant times to concentration of A and concentration of B. Means that the order of species A is equal to 1, while for B is also 1. So the overall order is equal to 1 plus 1 is equal to 2. So the half-life for the second order is equal to the concentration of T is half from the initial concentration A naught over 2, 50% from the initial concentration. So we replace this one with this value, so we can get this equation. So means that for the second order reactions, the half-life is inversely proportional to the initial reaction concentrations, and the half-life is shorter at the early stage. So for reaction to occur, the reactant must be collide and effective collisions must occur to ensure that the reaction is occur between the reactant, and then the reactant must be aligned properly or in a right orientations, and the energy should be equal or greater than the minimum energy or activation energy which is required to initiate a chemical reaction. Okay, you can see here for effective collision and effective collision. So you can see for effective collision, there is a reaction between a Cl and Cl after the collision process, while for ineffective collision, there is no reaction between the both Cl and this other reactant. So for reaction to occur, the reactant must collide in correct orientation and with enough energy. Means that the energy should be higher or equal to the activation energy. So we can see here how effective collision and ineffective collision.